this is post-process me. So yeah, let me stop me right there. This is unscripted, so this is more of a rambling video than actual good facts information. But since I didn't upload a video for quite a while, I was thinking I needed to do this. So this was done a bit quicker than normally, and I probably didn't even put this much time into this. So yeah, enjoy.
So yeah, the rocket project. So I talked about this in my stream for the Ariane launch that got delayed, just delayed. Yeah, rocket project. So I am required to do a project, in which I put 80 hours of work. So I will just talk about it, show some pictures, maybe show the actual calculations we have to do, and I'll put some pictures in what I used, links to websites, and so on and so on. So yeah, the rocket project itself. So we have to do a project with a certain subject. So me and a friend of mine decided to go and do a project, design a rocket that goes to orbit, and with physics, of course. And so we had to put 80 hours each into that. And the project needs to have an experiment. So yeah, that's what we need to do. So we started off with looking at the looking at what do we need to do? What because you need to go to work towards a goal of launching a rocket, or actually launching a payload into space. You need to have a certain goal. So what we decided to do was go and do this. Well, we decided to go and have a payload of 500 kilograms because satellites are getting smaller. So we wanted to do a 500 kilograms rocket, which is um, double the payload of the Electron rocket. So what you could do is have two mini satellites, like two 250 kilograms satellites, which are pretty small. But I guess that Earth observations are more getting towards smaller satellites because everything is getting smaller. Technology is advancing. So more and more companies, smaller companies that have want access to space have this. And we wanted to incorporate like new technologies like 3D printing, like the computer software engineering, making it on a computer, putting it to a printer, then printing this, so you have this rocket. So in the experiment, we want to show this, like that we can do this. But the rocket itself is, well, the design isn't finished, so I can't really show you anything because it is only still math, and it won't be built in real life because I don't have $1 billion laying around to start my own company to launch this. So what we did was we started off with, well, if you want to launch a payload, the rocket is what percentage of the total launch mass is rocket. So we went ahead and looked up the smaller satellite launch vehicles. So the Vector, the Vega, the Electron, there were more the one from Orbcom, the no, not Orbcom, Firefly, like the Firefly Alpha, the Firefly Beta, Then we well, more launches. I will put a whole list on what we looked for on to the side. But we saw this and we looked at it and we went like, well, what's the average percentage that the payload takes up? So I believe it worked out to be around. It was between 1% and 2%, and I believe it was between 1.5 and 1.9% that it was for us, like the average. So we took the average and then um, we multiplied that by the payload mass. So we eventually came up with 45.5 tons is what our launch vehicle is gonna weigh fully fueled on the pad. So then, once you have that, you can start and look at, well, what's the next important thing on your rocket, and of course the engines. So the engines are the next important thing on your rocket. Your rocket is propelled by those engines, and those burn fuel. So to exactly know how much fuel you need on your first stage and you need on your second stage, you need to know what are your engines going to burn, what are is do they need to produce on thrust, like what else do I need for to make these engines work. And of course, our engines are mathematics, so we don't know if they'll work in real life, but I expect with if I would have had $1 billion, I probably would have tested this and actually made it into a real launch vehicle because I really like this stuff. But then so we worked out and we started with the launch mass, and then to get on the pad, you want to have the thrust of your engines need to produce 1.2 times the weight of your rocket in thrust. So that worked out to be 80, I believe, 89 kilonewtons per engine. Um, because we decided to have 5 engines on the first stage, because then again you can have a failure happen in one of the engines. Because we wanted to have one engine out capability. And if you have only one engine, you'll fail. If you have 2 engines, your one engine can't gimbal enough to offset the thrust. So, no, 3 engines, same thing. 4 engines, same thing. Then we get to 5 engines, maybe, because 5 engines could gimbal enough. Well, 4 engines might be able to do it. I'm not sure about 3. I don't think so, because that would work out in a sort of triangle. Then one of them fails, then 2 of them need to adjust, which maybe could work, maybe not. But then we decided to. We could have gone for the 9 engines like on the Falcon 9, but I feel like I would have just been copying things. And then we decided 5 engines, fine, 5 engines, 1 engine out capability. But then for those 5 engines, instead of producing 89 kilonewtons of thrust, if one fails, you need to have 89 kilonewtons of spare thrust. So you have actually 6 engines on your rocket, but then the 6 engine gets taken out and the thrust of this gets divided over the other 5. So that's how it works out. So that amounted to 128 kilonewtons of thrust per engine. So we worked this out, and it is going to be a engine that operates at 89 bars of pressure. That's because, well, we are gonna use liquid oxygen and liquid methane, because specific impulse wise it is easier to use, well, not easier to use, but it is in performance between kerosene and hydrogen, and for hydrogen you need a lot of space, and by because hydrogen atoms are like hydrogen isn't really dense, and to solve this, why what first of all, why you want to use hydrogen, because hydrogen is really light, you can accelerate it really fast. The only product you get from combusting it is water, and you get a bit of spare hydrogen which you can accelerate really fast, and this amounts to a really high efficiency, which is what specific impulse is. Specific impulse is the impulse, the specific impulse is the efficiency, and it's in seconds. I don't know. I know why, because it is, you can accelerate a certain mass for that amount of time. You can have a certain amount of fuel, a certain mass you can accelerate for a certain time. That's what um the ISP turned out to be. So the higher the amount of seconds, the higher impulse is. But the downside of using hydrogen is that you need a lot of volume to get this. So your rockets are going to be really tall. And to get around this, you bind 4 hydrogen atoms to 1 carbon atom. So you get methane. And that's quite a lot denser. And the that's why you use it. The only downside is, of course, producing carbon dioxide, but it's cleaner than RP1, so the kerosene, which can also, if you use a certain type of engine, it can clog up your engine because of the soot it creates. So what we decided to do is methane, and then for the engine, why it operates at 68 bars, is there's this website. I'll put the diagrams we used for our math up here somewhere. Put it up here. Post processing me. And I could easily read out from those graphs what a certain type of thing needs to be, because the only way you're gonna find this out is by testing. But we can't really we can't test this, because for our experiment we would have liked to done it as close to the actual engine as possible, but we couldn't, because over here I can't really get liquid oxygen and liquid methane cheaply. It is, I'm still operating on a budget, because at the end, for the experiment, I didn't really pay on it myself. Well, it cost us a lot of money. It cost us over 200 euros to actually do this. So yeah, it's a lot. But the rocket itself, if you work out the math, it turned out to be, I believe, 1.7 meters long. Right about thing. I'll put it up here because I used a different program. I'll show the program right now. And I used this program eventually because I did it with a calculator. I calculated everything, and I wrote it down, and then to make sure I was correct, I used this program, and I turned out to be slightly off because the fuel flow I calculated was high.
Hi, this is post process me. So, looking at it again, I, for some reason, with calculating it with a calculator, I took the figures for 75 bars of pressure, and then for some reason, I don't know why, I need to figure out why I did it. In the program, I filled in 68 bars of pressure, so that contributes to the lower consumption of fuel, which I think is better because we have more fuel for the second stage left, more mass per jet for both stages. But I wasn't wrong. I just filled in the wrong thing for the second program, and it's probably because I figured that I could use different figures for um, the other engines, or I found different figures. I'm not really sure. I need to figure out what happened, but looking at it again, I wasn't wrong. I just did filled in the wrong thing in the program, which makes me quite certain I'm on the right track to completing this.
Higher than the program gave me, and I really trust this program because I use the light version, so the demo version. Um, but it is used, I believe, for students that actually make rockets. And so on to the project, like main project. This is like becoming a really long intro, but I like this. So moving it to the side, like while turning out the math eventually, because you need so for the second stage we would have one engine like on the Falcon 9, because you can have multiple engines, but once your second stage fills, there's no point, and the second stage engine is so wide that if you have multiple engines, um, you need to cut off the nozzle. So there isn't really a point of doing that because you can have more efficiency with one engine, lighter dry weight, so having a more efficient second stage. And so it turns out that that engine at its maximum width is going to be 1.7 meters wide. That sets the width of the rocket. So the width of the rocket is going to be 1.8 meters wide because want to have we don't want to cram it in there, so we want to have 5 centimeters on each side. So the rocket can actually push the second stage away and then free space. So we're thinking about that. So the fairing at its could be wider, it could be also slightly. It's also 1.8 meters wide. I need to check what the most for the 500/250 kilograms range, what the width of the satellite is, because we are gonna base the fairing on that, but I haven't checked it out because I'm still working on the project, as I said. But yeah, the rocket engine is going to be a sort of smaller size version, not of the actual engines, but it is going to be verifying the program because I tested it with the program. So how I how we set up the experiment engine. So how we set up the experiment engine is we are gonna make it a hybrid because we can get gaseous oxygen and we can get paraffin wax because that is a sort of a thing that's regularly used in making rocket engines, making hybrid rocket engines. And the plus side thing is because I could have done it with potassium nitrate and sugar, I know, but that we found that that was a bit too simple. And if we were going to use this, uh, I don't think I felt safe because when making this, you designed it at a certain pressure, and should something go wrong, you once you ignite it, you can't turn it off. There's no way of turning this off. So we went with a hybrid because with a hybrid you can turn off the oxidizer and it stops your engine, and then we're connecting a second gas line with CO2 connected to it so we can extinguish any fire immediately. So what we did, the engine is only going to be 10 centimeters high, or 13 centimeters high, and it's going to be a small engine. It's only going to be produce, I believe it was 0.2 kilonewtons, so not that much. Anyway, the engine is going to be strapped down. It's going to be static fire. Nothing is going to be flown because making it fly is another horrible thing to do. But then we're going to have active cooling to show that it works, and hopefully it's going to be 3D printed because what we tried, I will show it, is doing it in an oven at our school, but that didn't work out because I printed it from filament like this, and it turned out to be this at the end in the oven. It was all it was all charcoal at the end. So yeah, well, didn't work out. So I went to a company, like, hey, can you 3D print this for a reasonable price? And I haven't heard from them yet, but I hope they will reply soon. Um, but our project is basically going to be oxygen, paraffin wax, rocket engine, go. So the engine is going to be at 8 bars, and then the feed pressure of oxygen is going to be 10 bars, so you have a step down. And then there's not a lot of fuel going in there. It's only this wide, and I'm going to make a cylinder of paraffin wax. The paraffin will burn from inside out. Um, the oxygen will be fed through the bottom. There will be a blowback valve. I already have it. I will show you some pictures. I have 2 solenoid valves, and those can only handle 10 bars of pressure. So that's why the 10 bars is the feed pressure and 8 bars is the rock pressure. Because you can probably do it at 10 bars, but then I want to have a step down of pressure, so we have a nice flow of pressure going on, and we don't have constantly like spikes of pressure inside of the engine, which makes the blowback valve shut um, shut down. And I also want to have like the feed pressure step down, so if there is a spike, there's room for error, and it's all about safety. And then the 3D printed engine is going to be liquid cooled, so we'll have water flowing through it. So we show, well, that works, so the engine doesn't melt because it's still made of metal. But yeah, well, we're gonna have probably around around 2,000 degrees of exhaust, like the temperature. So that's how it works out, and this is gonna be this is the first explanation video. If I have more to update you about, I will do it. But yeah, well, that's it for now. And yeah, well, rocket projects. I have something really cool coming up though. I'll probably make another video about it because I'm still writing rocket talks 2. They don't go anywhere, but they take a long time, and I really need to make sure I have a good format going on, because I got some feedback on the other videos actually, and that's really good. I really need to work on making infographics work. I need to find out how to make that work, because last time it was a longer episode than normal, and it took me a lot of time to edit it. And it just takes me a lot of time, and since I'm doing this huge rocket project, it sucks up a lot of time. And then my free time, instead of spending hours behind my computer, I do want to make something with my hands, so I go to my regular hobby instead of making videos. I still do streams, but the videos are just on a low burner, and this is just sort of a quickly thrown together update video. Yeah, more to tell you. Well, yeah, the other thing I started to work, I ordered foam. I got a 3D printer recently. I did some rocket projects on that. I'm gonna make another Alfonso rocket fly, so he knows already about that. He is kind of helping me. But then I saw something really cool. Somebody printed a engine, like a turbine from a plane. The same turbine was used on the Virgin Galactic, or is used on the Virgin Galactic spaceship to mothership, the White Knight 2. So in my mind, I got this crazy idea to make the spaceship 2 from Virgin Galactic and fly it. And I ordered my foam. I'm working on it on Illustrator, and it's gonna be really cool. It's gonna be quite big, but I believe it's gonna work this time because I really did my research on, well, what does work for flying planes and what doesn't. So yeah, expect something coming up on that soon, or maybe soonish. Like soon can be like 8 months, a year, because I know I have a rocket that I time lapsed. That was the Soyuz, and I still haven't finished it. I really need to do it, but yeah, time is not. I don't really have a lot of time because school sucks up a lot of it, and I know school goes first. But yeah, long video rambling about me, but yeah, at Astra, and I will do uploads on videos on the rocket engine because that's a real cool project. So once I know more about the rocket project, or if I have the rocket in my, like the rocket engine actually there, I will make another video about it. And yeah, well, see you later. Next streams, next videos, rocket talk, whatever you watch. Subscribe and see you for more. So yeah, well, bye.